Okay, so these notes are about limits using tables and graphs. This is our notation that we're going to use. And the way we say it is the limit as x approaches c of f of x is equal to n. Okay, that's how you read that. Typically, there would be a number put in here for c, and typically the answer would be a number. This might be a function. Okay, so what limits are is they mean as the x value gets closer and closer to the c value, do the y values get closer and closer to the n value. The key with the limits is that you don't actually have to equal them. You just have to be able to get closer and closer. So it's not necessarily the same thing as the function. It's talking about as you get closer. We're going to look at limits graphically first. So on this one, I've given you a graph. I could ask you, there's a point right here. I could ask you, what's f of 1? F of 1 is 2. That means what's the function value when x equals 1 and the y value of the point is 2? I could also ask you, what's the limit as x approaches 1 of f of x? That means where is the function going towards? So if I put my right finger on the right side of the graph and I went towards x equals 1, my y value would be getting closer to 2. And on the left side, my y value would be getting closer to 2. So since both fingers come to the same place, the limit is equal to 2. So in this case, the function and the limit are the same thing, all right, because it's nice and smooth and continuous. All right, in the second picture, if we were talking about f of 1 does not exist because it's a hole, right? There's a hole in the graph, so the function doesn't exist. But when we talk about the limit as x approaches 1 of f of x, we're talking about where is the function going. On the right side, as I get closer and closer, my y values get closer and closer to 2. On the left side, as I get closer and closer to x equals 1, my y values get closer and closer to 2. So the limit as x approaches 1 is equal to 2. So in this one, the limit exists even though the function doesn't. If I were driving along the road of the function, my y values would get closer and closer to 2, even though they never actually equal it. All right, in this next example, if I find f of 1, that's where is the function at 1. F of 1 is equal to 1 because that's the y value of the solid point. But if I went to look at the limit as x approaches 1 of f of x, the right side of my graph is going to a y value of 1. The left side of my graph is going to a y value of 2. So for this one, we say the limit does not exist because the left side and the right side, or the left side approaches a different number than the right side. So a lot of times when we ask you for limits, we'll ask you what are they, and you could just say that it does not exist. And oftentimes we'll ask you for justification, and then you'd have to say how come and write out some sort of verbal explanation. So this picture was an example of where the function existed and the limit didn't. Okay, so sometimes they're the same, the function and the limit, but other times they're different. Okay, on this one, the function exists. That's where the solid dot is. F of 2 is equal to 3. But if I did the limit as x approaches 2 of f of x, that's where is the road going. As I drive towards x equals 2 from the right, my y value goes to 1. As I drive towards x equals 2 from the left, my y value equals 1. So the limit is equal to 1. So in this one, both the limit and the function exist, but they're two different numbers. Okay, in this next one, at x equals 1, we have an asymptote. So here, f of 1 does not exist because it's an asymptote. Right. Now what happens as we do the limit as x approaches 1 of f of x? So on the right side, I'm headed down towards negative infinity. On the left side, I'm headed up towards positive infinity. So for this one, the limit does not exist because the left side does not equal the right side. Okay. And I don't usually use a lot of abbreviations, but it is kind of common to say like LHS does not equal RHS for the left-hand side, does not equal the right-hand side, if you don't want to write out all the words. If it were on like an AP Calculus exam, you'd probably want to write out all the words, but I'm okay with the abbreviation. Okay, so in this next one, again, my f of 1 does not exist because it's an asymptote. But when I go to do the limit for this one, it's a little different. The limit as x approaches 1 of f of x. On the right side, I'm going up to infinity. And on the left side, I'm going up to infinity. So both sides are going the same direction. But infinity can't be a limit because the whole point of infinity is that it's limitless. So it sort of depends what book you have. We're going to say two things. We're going to say it approaches infinity, and we're going to say that it does not exist. Because infinity is not a limit. That's the whole concept, that infinity is limitless. Some books will say, instead of the arrow for approaches, they'll say it equals infinity. I don't usually say things equal infinity because you can't actually ever equal infinity. You could always be more. So we're also going to do limits numerically or from tables. So when we ever have to make a table, we're always going to have a calculator. And what we'll do is we'll just go and put it in our y equals. So I would put it in using the fraction button. So my function is x squared minus 49, sorry, over x minus 7. And then I'm going to make my table. So I go to second table. My calculator is set up the way most of yours are set up from the beginning, which is where you just go up and down and it gives you all the numbers in the table. We want to change that because we need to be able to put our own numbers in the table. So if you go to second table set, we can go down and we can change our independent variable, or our x, to ask. And then when we make the table, it's going to be empty. And we'll leave our dependent, or our y, on automatic so that it fills in y based on x. Okay, so I'm going to make my table. And this is sort of my evidence of how I'm going to get my limit. And what I'm looking for is what happens around x equals 7. So it doesn't really matter exactly what the y value is at 7. If I type that into my calculator right now, a y of 7, it's going to tell me that there's an error because the function doesn't exist at 7. Okay. The question is, even though the function doesn't exist, could the limit possibly exist? So when we say we're going to get close to 7 for a number, we're talking about getting really close, like 6.999. That's really close to 7. Usually the numbers I put in would be like 6.9, 6.99, 6.999. So I'm getting very close to 7. And then on the right side of 7, it would be like 7.001, 7.01, 7.1. So my x values get closer and closer to 7 from the right. My y values get closer and closer to 7 on the left. And now I need to, my x values get closer and closer to 7 on the left. I want to see what happens over here on the right side. So I need to make my table. So for my x values, I'm going to start over at the top again. I'm going to put in 6.9, then 6.99, and 6.999. It doesn't really matter what 7 was. We already found that was an error. 7.001, 7.01, and 7.1. One of the things you want to realize is there's a limited amount of space up here on the screen. So sometimes if you go over to the actual y values, you can see the full decimal down there on the bottom. So if it looks like it's rounding, you might want to look at the full decimal value. Okay. For these, the whole decimal fit on the screen. So my y values to put over here in my table would be 13.9, 13.99, 13.999. So it looks like the y is approaching 14 on the right side, right? The closer we get to 7 for x, the closer y is going to get to 14. And then on the right side, I had a bunch of 14s. So as x came in towards 7 on the right, my y was still approaching 14. So the answer to the problem is that it equals 14, because the left-hand side and the right-hand side are both going to y equals 14. It doesn't matter that it never actually gets there. That's a hole in the graph. And you could go through and do it algebraically and reduce, and we'll do that when we do algebraic limits. But for now, this is showing numeric evidence. Okay, the last example here is one where I give you the table. So you wouldn't have any algebraic function that you would type in. You'd just be looking at the table. So this part of the table, x is getting closer and closer to 2 on the left side. This part of the table, x is getting closer to 2 on the right side. So as we look down here, what is y doing? Y starts at 16, then it goes to 182. This one looks like y is shooting up in the air towards infinity. Whereas this side on the right, it looks like y is heading down towards negative infinity. Oops, negative infinity. So for this one, we would say the limit does not exist. Again, the left does not equal the right. They're going two different sides. So the limit doesn't exist. And I have to be able to do these without a calculator if I were given the table. Okay? So if you're ever asked to make the table by yourself, you'll be given a calculator. You should be able to do graphically if I give you the graph, or if you have to make your own graph and then answer it.